All right, let's go ahead and get started. Any questions before we get back into anything? Okay, so I think there's a written homework due tonight. And what else? Oh yeah, I don't have office hours today, but starting Monday I will every Wednesday, every Friday. So that Math Community Center opens up next Monday. So yeah, if you need anything, I'll be in there after class on Wednesday and Friday. Not directly after class, but on both those days. All right, so we're talking about trig integrals. So basically, if we kind of recap the things we did on Wednesday, a big part of what we do for these is I think actually exclusively, we've tried to set up substitutions. So either that was a substitution by using a Pythagorean identity to rewrite a sine squared as a cosine squared or vice versa. Or I think one of these we used a double angle identity. So if you haven't already, I would make sure you know, like basically have like a place in your notes where you're going to write down all those identities, because not really worth committing to memory unless it happens organically. But basically just have a place where you can refer to them. So since we're talking about Pythagorean identities, we talked a lot about like this primary one, sine squared plus cosine squared equals 1. But from here, we can generate some additional identities as well. So one thing I want to do here is if I divide both sides of this by cosine squared of x, what do I get? So if I make that division, what happens?
Sine squared of x plus 1 plus secant squared of x.
How do you feel about that? So this is another one that has uses as well. So looks very different, but really comes from the same place here. What if instead of dividing by cosine, where's my erase button? Oh, I have it. Okay, I don't know what's going on. Anyway, what if instead of dividing by cosine squared, I divide by sine squared of x? 1 plus cotangent squared of x equals cosecant squared of x. So again, I would have these so where you can refer to them as well. These have a lot of uses as well for where we're going. Any questions about where these come from? Okay, so let's start trying to make use of one of them. So I want to do this integral here. The integral of tangent to the 6th of x times secant to the 4th of x. So the overall goal is very similar to what it was. We're going to try to set up a substitution. So we might have to do some manipulations on the way there, but here's the question we want to answer at some point. What does u equal? So what's our substitution going to be? And then what's that du going to be as a consequence that comes from that? So let's just remind ourselves, how are u and du related to each other? They're derivatives. One's the derivative of the other. One's an integral of the other. Do we know any relationships between tangent and secant?
Is this one also missing the x?
Yes, it is. I'm sorry. I'd like to blame somebody else, but this is my fault. Do we know any relationships between tangent and secant?
Square of it, tan of x, the derivative secant squared of x.
So here's something we know. We know that the derivative of tangent x is equal to secant squared of x, right? What if we go the other way? That one's secant x tangent x. So not as simple as sine and cosine. Those derivatives are a lot more straightforward, but basically these two things right here are going to basically dictate how we set up a substitution. So basically we're going to go one of two directions. Either we're going to have u being some form of tangent x, or u being some form of secant x. Is it clear at all which one of these substitutions we might want to do? So it's probably not obvious yet, nor do I think it should be. But are there any kind of transformations we can make? So right now we have tangent to the sixth and secant to the fourth of x. Based on these new identities we just talked about, especially this one here, we can start making, like, we can start exchanging, even powers of secant for even powers of tangent and so on. So can we start doing something like that? Which direction do you want to go? Which way, or
Secant of x.
what's that?
U equals secant of x.
So if you want to try using u equals secant of x, basically what we have to do is this. For us to use this substitution method, basically we're going to have some secant of x's we can call u. But then we're going to have a secant x tangent x to call our du, right? So let me ask this, and let's just talk about, strategy. If I have, so the fact that I have a secant to the fourth of x, right? I can just call that u to the fourth. Is that okay to call that u to the fourth? That's no problem, but then, so let's just start going that way and see how it works out. Tangent to the sixth of x times u to the fourth dx. Is there a way to get the du we need? Is there a way to get secant x tangent x dx? So it's clearly not there now, but could we get there?
Yes.
How?
You think a tangent squared x out of tangent 6x.
Okay, so that's something we can definitely do. So I'm going to write this as tangent to the fourth of x times tangent squared of x u to the fourth dx. I'm assuming you wanted to pull this out so we could transform it. What does that become?
Secant squared x.
Is that going to, so do we have the du now?
Distribute that, then it won't be just one.
Right, and that's the thing that I was hoping we get to is, so for the du we need a single power of secant x, a single power of tangent x. So we're starting with tangent to the sixth and secant to the fourth. And think about the way that Pythagorean identity, like what it allows us to do. Am I ever going to be left with simply a secant x and a tangent x? Yes or no? Why is that impossible?
Because the identity only goes to square.
The identity only does squares, right? And what are my powers here? What's true about 6 and 4 that makes this impossible? They're even. They're multiples of 2. So because of that, I don't think I'm ever going to get to secant x tangent x. So I want to pause there and make sure that we're okay with the argument that I'm making. Because the Pythagorean identity only allows us to deal in powers of 2 at a time, and I have evens, I can take secant to the fourth down to 2 or down to 0, but I can't ever have 1. So because of that, I don't think this works. So let's try having u being tangent x. So let's just start doing the substitution. This becomes u to the sixth, secant to the fourth of x dx, right? So I got the secant to the, basically I got a bunch of x stuff I still have to mess with. What can I do with that secant to the fourth of x?
Split it into two secant squared.
Okay, so this becomes u to the sixth secant squared of x, secant squared of x. Why did you do that? Why did we split that up?
Then substitute the secant squared of x dx with du. And
Okay.
base secant squared of x with 1.
So what's the identity? Secant squared x equals tangent squared x plus 1. So yeah, one of those is going to go to that purpose. So 1 plus tangent squared of x. The other one is going to be du, right? So any questions why the things we are doing? Are we feeling better about this? Okay, so the 1 plus tangent squared of x, what does that become? So u to the sixth times 1 plus u squared du. So I think now the job is, I mean, one of our primary jobs is done. Substitution is complete. Is this an integral we can do? What is it? Or where do I go from here?
1/7 plus 1/8
Okay, so let's do this first. The integral of u to the sixth plus u to the eighth du, and that's equal to what?
1/7 e to the 1/9.
Plus c, and then what's our u? What I can't remember what we did. Tangent squared, right?
Just tangent, right?
Oh yeah, so it's 1/7 tangent to the seventh of x plus 1/9 to the tangent times tangent to the ninth of x plus c. So questions about what we ended up with. One thing I think it's really worth pointing out here is why we did this. Why did we use this scheme as opposed to the one I crossed out? What made that decision for us? Even powers on tangent and secant, right? Does it matter that they were both even? I think tangent couldn't have been odd. All we really need to make this work is we need an even power on secant because we need to be left with 2 powers of secant. But I think if this is tangent to the ninth, we're still going to be able to get that as long as you have an even power on secant. So something to look for. And just like we saw with sine and cosine last time, the parity, the even or odd nature of those powers is really what drives the decision we make. So keep that in mind for this one. So again, we're looking at these same relationships. Basically, what's the derivative of tangent x? And what's the derivative of secant x? So which way do we want to go this time? So u equals secant x, which means du is secant x tangent x. So I'll ask the same question I did last time. Are we going to be able to be left with a secant x tangent x in this case, right? And why is that? What's odd? Both powers. So in this case, I do need both to be odd because I'm trying to get to a single power of secant, a single power of tangent. So because of that, I need them both to be odd. All right, so now that we've decided on that u and du, let's start rewriting this integral. How's it gonna look? Or tell me what's right.
7 times get to the 4th of x.
Times tangent to the 4th? You said u to the 7 times tangent to the 4th?
Yeah, I want to split the tangent into
Okay, let's try this. We okay with that? Right, that's yeah, so yes, secant to the 7th is u to the 7th, but we should leave one of those handy for the du we know we're going to need. So I'm gonna pull back a little bit and do this. U to the 6th times tangent to the 4th of x times secant x tangent x dx. So I see my du in there. So maybe I'll actually make that clear. This is now u to the 6th tangent to the 4th of x du. This is terrible. Every single step. All right. So we have one last thing we have to deal with. So how do we deal with that? Right. When you say twice. Okay. So this is going to become secant squared of x minus 1 all squared. Okay. Du. Which, if we apply our substitution again, u to the 6th times u squared minus 1 squared du. Right, are we okay with that? So I think this is now totally transformed. So the substitution part of this is done. So what do we need to do now? Can we integrate from here? Might need to do a little bit more algebra. So what does this inside of this bracket be, or what does this bracket become? U minus 2 times u squared times 1 plus 1. All right, one more expansion. U to the 10th minus 2u to the 8th plus u to the 6th du. All right, I think that's as far as that's as simple as we're gonna get. So what is this integral? 1/11th u to the 11th. You have, oh, I'm sorry, this is a,
oh, sorry.
This is 8.
8, yeah. So 2/9.
2/9 u to the 9th plus 1/7 u to the 7th plus c. So 1/11th secant the 11th of x minus 2/9 secant to the 9th of x plus 1/7 secant to the 7th of x plus c. All right. Questions?
But this is kind of taking a step back, but I kind of forgot. Can you explain the whole idea between the odd and even powers?
Yeah, absolutely. So really the question, basically the thing we have to look at, the reason these even and odd powers matter, it all comes to basically which of these two choices are you going to make. Choice A, which is this u equals secant x, and choice B, which we didn't write down, but I should now, u equals tangent x, du equals secant squared of x. So basically, knowing that we're trying to work toward a substitution, once we choose something for u, the du gets chosen for us. So basically, what we're looking for is this. Am I going to be able to get to secant to the 1st tangent to the 1st of x? Basically, here's what I believe. I believe the answer to one of these will be, I might be able to do one of these. I might be able to do the other. I will never be able to do both. Because the fact that one of these is secant squared, one of these is an even power of secant, the other one's an odd power of secant. So because the Pythagorean identities only allow us to basically transform secant squareds into tangent squareds and vice versa, basically whatever parity we have, so the fact that this is odd and this is odd, we're stuck with that the whole time. So that's what dictates the fact that we need an odd, so we're going to go towards the du that needs an odd power of secant and an odd power of tangent. Yeah, I wouldn't say more likely. I think you're kind of stuck with it. Do you have a question?
I was just gonna say, just like on the last one, we only needed secant to be even. For the one we just did, wouldn't only tangent have to be odd? Because secant turned into u to the sixth. If it had been like u to the fifth instead, like it could have been odd at the beginning.
Secant could have been odd in the beginning?
Yeah. Because if it was like secant to the sixth, that just means that the u at the end would have been u to the fifth. And then it just would have multiplied out. So only tangent has to be odd.
But what about the fact that we needed this, right?
Yeah.
So I think because of that, because we need a single secant and a single tangent, I think that means we need both of these to be odd, right? Oh, wait. No, I agree.
Yeah,
You're right.
So
okay.
If you're trying to use tangent as u, you need secant to be even.
Okay.
Or odd. And then if you're using secant as
okay. So you're right. You're very right. So they're both only depend on the parity of one of them, because, and I think this kind of accidentally is evidence for her argument, is that the fact that we had u to the seventh was not a problem. The fact is that we didn't have a secant, that we didn't leave ourselves a secant to refer to as du. So yeah, so let's recap here. What did I need to be even for this one? Secant, the power of secant only, right? And for this one, I needed the power of tangent only to be odd.
Essentially what's left over.
Yeah, basically, and that's the bottom line, is it's not the u that dictates which method you take, it's the du that comes off of that. So in this case, we required secant to be even. This one requires tangent to be odd. Is it possible to meet neither of those things? I think it's very possible for neither one of those to be true. It's very possible for both of them to be true too. So you might have more, depending on what you're given, you might have more choice than you think. Go ahead.
Going back to like the second step, instead of trying like the tangent into secant squared x minus 1, would you not have been able to like take all four of like the tangents and like four of the u's and then make it like secant x tan x like 4 times?
Secant x tangent x 4 times. So basically you would have okay, let me be clear. What step, or I want to make sure I know what step you're talking about. So are we talking about like from here?
No. So right when you, yeah, that one, and then the next step you turn it into secant squared x minus 1 squared.
Okay. Okay, so from here to here?
Yeah.
So what are you suggesting we might do instead?
Well, I just don't understand. Could you also like take 4 of the tans and then 4 of the u's and make it, you know, u squared and then secant x tan x 4 times?
That sounds to me like you're going to have four powers of du.
Yeah, that would make it du. So would you?
But so that's
keep du only 1.
Yeah. So and that's again, this all comes back to the idea of a Riemann sum, which this looks way more sophisticated than this. But basically, what an integral is doing is this: finding the area of rectangles. I mean, I can have as many rectangles as I want, but really I'm taking areas of rectangles and adding them together. And to find the areas of those, I need a height, which is usually given by like what the value of the function is. And I need a base length, which is du. So because of that, and I know I kind of harped on this a little bit, is that you don't want to divide by du because of this, but I also don't want to multiply by du any more than one time. So that, I'm glad that came up. Yeah, we need du to be something we multiply by, and we also need it to be linear. We need it to be power of 1 and nothing else. Any other questions? Okay. So we kind of talked about the parity of things. Is tangent even or odd here? Even or odd power? Is secant even or odd? It's even. What's the power on secant here? 0. 0 is an even number. So subtle, but we don't have a secant here. So based on the things we've talked about, which way are we going? So we talked about basically for one of our schemes, we need secant to be even, right? For other one, we need tangent to be odd. So which one of those do we have? The latter, right? So we have tangent being odd, which tells us what? Which way do we go for u? U is secant of x, and du is equal to secant x tangent x dx. I'm so ashamed of my slide. Go ahead.
So, where are you getting the secant from?
That's a very good question. It's not there, right?
Yeah.
So, I mean, it's not there, but could it be?
No, it's not there. So where did you get it?
0.
So when I say could it be there, for example, this one here, this one might, I could have started this with a tangent to the 10th and no secants involved, right? Why do I say that? Yeah, and what allows us to do that? Yeah, so basically these things here, right? So this identity here, basically if I have tangent to the 2nd power, yeah, I don't see the letters SEC written in there, but I can re-express that so that basically I am dealing with the secant function. Same with sines and cosines. So yes, in this example we're looking at, we are looking at something that does not have secants in it. But could we rewrite it so that it did? In fact, I don't want to say it's the only way to do this integral, but I think it might be the most direct, might be the most efficient way to get there. So right now I cannot make this u substitution. I cannot find this du. So if we can do a rewrite to make those things appear, I think that'd be a good move. Can we try doing that? How do we try to do that? Tan squared x, tan x. So yes, I can split these powers apart. Tangent squared of x times tangent of x dx. Then what? Okay, so what does tangent squared of x become? So secant square root of x minus 1 all times tangent of x dx. So now we have secants explicitly there. Did that help?
What do you do with the leftover tangent of x?
Oh, that's a good question. Let's worry about that after we write it. So this becomes secant squared of x, tangent of x. Let's actually just rewrite this as 2 integrals, minus tangent of x dx. Is this integral on the left something we can start using the substitution on? So it's kind of strange, but I think this one became, would we agree that secant squared x tangent x dx is the same as secant x, tangent x dx? So I think this one on the left became u du. Go ahead. What's that? Good question. So, and I'll confess this, I never can remember I can't remember the tangent and secant ones with any confidence. So pretty much what I do in my head, or I write it in every time, is I know this one for sure, right? So how do I get secants, or how do I get tangents and secants to come out of it? I'm going to divide everything by cosine squared. And if I do that, I get tangent squared of x plus 1 equals secant squared of x.
And then you just solve for.
Yeah, if you isolate secant squared, you get a tangent squared of x minus 1. Yeah, thank you. Wait, yeah. I just rewrote it.
Yeah.
You ever have 2 steps in your head that you're going to do, and then you just combine them into something that doesn't make sense at all? Okay, so that's where that came from. And again, if I'm not memorizing that, I don't expect you to either. But the Pythagorean identity, like the fundamental one that comes from sines and cosines, you can use that to build up all the other ones. Good question. So this integral u du is simple. We could do that one. How do we handle the tangent of x one? Right, and that's one thing I was hoping would come up is this. We've spent so much time talking about trig substitutions and how to do certain things that at some point it could conceal the fact that there are other things you know how to do. So this is something we've done through substitution before. I'm out of control. Sine of x over cosine of x. So that's an integral we can do, right? How do we do that integral? That is a substitution. I think we've done that exact one a couple of times, right? So would it offend anybody if I just called it natural log of absolute value of cosine of x? I think that actually came up on Wednesday, that exact integral. What's the integral of u du? Wait, sorry.
Plus, I believe.
Is it negative? Yeah, right. Yep. What's the integral of u du? 1/2 u squared. So I get 1/2 u squared plus this thing plus c. And last, let's undo the substitution. So 1/2 of secant squared of x plus natural log of cosine x plus c.
Is that considered an integration by parts?
No, and that's a good question. So I really don't like the name integration by parts because it doesn't really make clear why it's done. Integration by parts is more for like, I think even the way I introduced it was like undoing the product rule. Product rule is a great name. It tells you exactly when you use it. Integration by parts, I don't think is that good of a name. But the fact that I was able to split that integral up, that comes from, I mean, that's because these things are added together that I'm allowed to do that. So I think by definition, it's not integration by parts, but take advantage of the fact that when you're taking the integral of a bunch of things that are added together, you can handle them turn by turn by turn. And I think that's something you probably do without knowing it. So like, if I ask you for the derivative of x to the 4th plus e to the x, how do you do that? Yeah, you don't think about that all at once. All right, any other questions? Could we have done this with u being tangent of x? Let's think about it. If u is tangent of x, then this integral becomes, I wish I could buy myself some more space. So I'll just use this little. So let's think about it. If u is equal to tangent of x, then what's du? Secant squared of x dx, right? So then this becomes,
Well, the next one we expanded to secant squared of x minus 1 times tan x.
yeah, so I don't know if you're gonna get a dx everywhere. So I think this one right here becomes, yeah, this one could become u du for the same reason, right?
So when our final answer also be what tan squared x.
Yeah, so the basically the thing's gonna make it different is this constant. Because basically it's gonna be different by like a -1. This is gonna sound like a really BS answer, but I promise it's not. So if we went that way, then basically what's the difference between secant squared of x and tangent squared of x? They're off by 1, right? That's all in the identity. That's the only thing that makes them different, right? Is that one is one larger than the other. So because of that, when we finish this integral, we have no idea what this mystery constant is, right? Basically, that hides the difference. Whatever that, if we had enough information to solve for that constant, in one case it would be one larger, in the other case it would be one smaller.
So both would be correct.
Yeah, because the fact that I have no idea what this constant is, sort of saves me. Let me ask this question here. We just got done taking this integral. We've taken lots of integrals like this. How many functions are like at the bottom of this page here? How many functions are written here? Is it just the one? Is it 2? Is it more? It's an infinite number. Because since I don't know what this C is, basically all I can say is that the integral of this is a function that looks like this, but I don't know, like if I were to graph it, I don't know if I like how high or how low I have to shift it. I think I could really convince you if I made this a definite integral. Yeah, let me think about that. Maybe I'll do that and post it on Canvas or something. But the fact that you could go both ways and it looks like they'd be different answers, but they would be off by a constant, which that plus C allows for. Anything else? All right, so let's get away from stuff that's obviously trig for just a minute. Is this right here an integral you could do? Do you have a question? Yes, yeah.
I said this one looks like one of the ones on like the web.
Okay, good.
Because I was sort of confused.
That you were not able to do yet, probably?
No.
Yeah. Yes, and here's why, because we haven't talked about it. This right here, is this an integral you can do? I believe we could do this one with things we've already talked about. Like, how would we go after it? We won't finish it, but you could do substitution. What's a good U? And what's a good du? -2x dx. So I think I have my u under the radical. X dx is not the same as my du, but it's off by a constant. So I could manipulate that and get to where I want to go. So that is something you can do, right? The fact that you have that x multiplied by the radical means that substitution is open to you. But what about this thing here? Is this something you could do? There's probably one on the web that looks exactly like this. That if you've looked at it, you have no idea what to do. So this right here is deeply, deeply not obvious. That's a trig integral right there. Go ahead.
Is it an inverse trig?
It's not even inverse trig. It's just it's very, very not intuitive, but it's an application of using trig. And the one thing I will say is this. Okay, we're doing the exact one. Okay. So what makes this hard to do? What's that? You can't get a du, right? But like, what if it was square root of x squared dx? Is that possible? That's fine, right? That just becomes x dx. So here's what I would love to do. I would love to come up with some kind of a substitution that I could put in for x that eventually lets me only have one term in that radical. because then that's a lot easier. The fact that I have two terms added together under a radical makes things really tough. So I already kind of alluded to this. We're going to set this up as a trig function. So x equals something of theta. So let's just try our favorite trig function. What do you got? Just pick one. Sine sounds good. Why'd you choose sine? What's that? Yeah, but how did you all choose the same one? There are like 6 of them. Okay, so kind of wanted to see something that wouldn't work, so we're not going to. So we'll do sine, which I promise will work, and then I'll pick one that won't. So let's do that. I want to make x equal sine theta. But integration by substitution means that that's not the only choice that matters. There's a dx that comes from there, right? Cosine theta, d theta. So let's use this substitution to rewrite this integral. This becomes 1 minus sine squared theta times cosine theta d theta. Was that helpful? Yes, but why?
Substitute 1 minus sine squared of theta for cosine squared.
And that's kind of the goal with these very non-intuitive trig substitutions, is that 1 minus sine squared theta can be rewritten as cosine squared theta. So that comes directly from this trig identity. Sine squared of theta plus cosine squared of theta equals 1. So now I can't take the square root of this. I can't like simplify that. But can I simplify the square root of cosine squared of theta? Absolutely. So this becomes cosine squared of theta d theta. Is that an integral you can do? Did we do this exact one last time, or was it like sine squared? Okay, so how did we do that sine squared? That one need a double angle identity. Somebody asked me this after class, and I didn't talk about it with all of you, so I think we should do that now. Can I use a substitution on this? Why is substitution not going to work?
Two terms that both the derivative and the.
Right, and that's the point. Is like whatever you come up with for u, like what's a u we might try here? Cosine theta, then what's du? Negative sine theta d theta. I'm not going to get that negative sine theta to appear for me. So because of that missing sign, I'm not going to get substitution here. But what I can do is this. I know these double angle identities, which I hope you wrote down. I'll just write down the one that I'm going to write down the one that involves cosine squared without sine squared, which is 2 cosine squared of theta minus 1. So yeah, I'm going to use this identity here. How does that thing allow us to rewrite this integral? Yep, so 1/2 cosine 2 theta plus 1 d theta. So I'm going to stop there before we do that integral. Questions about anything, though? I mean, here's kind of a bad thing that you all kind of guessed the right answer on this one to start. Do we have an idea why sine would have worked where tangent would not have helped?
There's no identity for.
So let's even look at u equals tangent theta. If u equals tangent theta, then what's du? Sorry, x. Secant squared theta d theta. Then if I rewrite the integral, I'm going to have the integral of 1 minus tangent squared theta. Secant squared theta d theta. Can I rewrite 1 minus tangent squared theta in anything useful? I think if it was 1 plus tangent squared, I'd be happy, right? That's true, right? So yeah, if it was tangent squared minus 1, that'd be secant squared, right? So the fact that that sign is not what I need it to be, that's not going to help. So basically, that's kind of what I'm leading up to here, is that for you to decide what trig function to use, it's really the question to ask yourselves, I think, is this: what is going to help me get that expression under the radical to be a single term? Because then you'll actually be able to simplify it. Any more questions about how we got there? All right, can we do this integral? What is it? Or do we want to rewrite it first before we start diving into it?
It's -1/4 sine of 2 theta plus 1/2 theta.
Okay, are we sure? I think this is a positive here. The derivative of cosine is negative sine, but going. All right, this is one of those weird cases, though. I mean, it doesn't really bug me because I don't want to do it, but for some reason, you're not really expected to undo this substitution. So basically, when you're asked about things like this on web work and on test and whatever else, even though I gave you an integral that was written in X and you substituted away from that, don't worry about going backwards. Questions? I see a lot of Ten's eyebrows, so I feel like there are questions. The last step there? Yeah, absolutely. So let's break this down. And I want to know why my eraser's not working today. Is there any chance I can undo stuff? No, of course not. So let's start by pulling out the half. So 1/2 of the integral cosine 2 theta plus 1 d theta. I'm gonna assume that the most difficult part of this is how to deal with this integral of cosine 2 theta. What's the derivative of cosine 2 theta? Yeah, I'm saying the derivative. It'd be -2 sine 2 theta, right? So because of how we have to treat the chain rule, when you take a derivative, you take the derivative of the cosine and more or less ignore the argument to the cosine. So that becomes -sine 2 theta. But then you have to multiply by the derivative of that inside argument, right? That's where the 2 comes from. So when you take a derivative, you have to multiply by that constant. When you take an integral, you end up dividing by that constant, which is where this 1/2 times 1/2 sine 2 theta comes from. And then what's the integral of 1? For us, it's theta. We're integrating with respect to theta now. So that's where all that stuff came from. So basically, these 2 intermediate steps are what led to the thing I boxed in. I got like 1 minute left. Any last minute questions on this example or anything else before we go? All right, so we'll do more of this on Monday. Otherwise, have a good weekend.